All right, we're going to finish off uh, the modules 21 and 22 lectures by talking about the SN1 and E1 reactions. Okay, um, so let's consider a situation where I have a tertiary halide, um, and I just put it in a solvent that could be nucleophilic. So in this case, I'm going to leave it in a solvent of ethanol and just let it sit there for a while. Um, If I do that, it turns out that I end up producing two products, one of which is not shown correctly on the slide, so I'm going to fix it. Um, so one of which looks this way. Uh, this is a substitution product. So this first one would be a substitution. And the second one, I'm just going to fix that double bond. The second one would be an elimination product. But you hopefully have the tools now where you can look at this and say, well, I don't think that substitution was an SN2, and I don't think that elimination was an E2. I'll give you a second to think about it. So why couldn't this be SN2? Well, to be SN2, I need a good nucleophile. And good sterics. Here I've got ethanol, which is kind of a weak nucleophile, and a tertiary halide, so I have bad sterics. So SN2 is ruled out. Okay, why couldn't it be E2? Well, I know E2 requires a strong base. But in this case, ethanol, not only is it a weak nucleophile, it's also a weak base. Its conjugate acid pK is like -2. So we don't have a strong base, couldn't be E2. So how can this reaction even happen? Well, to come up with a mechanism, this hint may or may not be meaningful to you, but the hint is that the rate law for this reaction only involves the substrate molecule. So in other words, it doesn't matter how much ethanol I add. All that matters is the concentration of my tert-butyl bromide in this case. What that tells me is that my rate limiting step in this mechanism only involves my tert-butyl bromide. So I need to come up with a mechanism that only involves that in the rate limiting step. So I sometimes like to personify molecules. So here's the way I'm going to describe this. Um, you know, I have tert-butyl bromide, and I know that every bond is constantly vibrating. Um, so bromine in this case is in a relationship with carbon, but bonds vibrate on their own. So sometimes that bond gets a little longer, sometimes that bond gets a little shorter. Um, there's vibration going on. So sometimes the relationship's going well, sometimes it's going less well. Occasionally, depending on how much kinetic energy the molecule has, um, the bond will get to the point in a certain small fraction of the molecules where the bond just breaks on its own. In other words, every once in a while, bromine will take off as a leaving group on its own and leave behind a carbocation. Think of this as just bond vibration taken to the extreme. Okay, The hotter my solution is, the more likely this is to happen because the more kinetic energy the molecules are going to have. Um, but even at room temperature, there will be some small percentage of molecules where this will happen. Now, most of the time, bromine takes off, realizes its mistake, and most of the time, bromine will just come right back if it can. But if my solvent is something that might not be a great nucleophile, but can act as a nucleophile, remember that my molecule is surrounded by solvent. So if I have lots of ethanol molecules around and they're all over, then once bromine leaves, it's likely that this carbocation, which is now screaming for electrons, is going to look for a shoulder to cry on. It's going to look for someone to come and share electrons with it. It's really likely that one of these ethanol molecules might be the first thing to come along and offer its electrons. If it does, then I have this intermediate, which we've seen before, this oxygen with a positive charge. This has a strongly acidic hydrogen, which means anything can come along and deprotonate it. So this is a situation where I can say better call Sol and have the solvent come and deprotonate. And lo and behold, that gives me my substitution product. So I can get the substitution product when I form a carbocation, the ethanol jumps in, forms a bond, and then gets stuck there. Okay. I say I like to personify, I think of this as the solvent is playing the friend strategy. It knows it's not a super confident nucleophile that can go in and kick out the leaving group. But it also knows if I hang around, if I bide my time, eventually I know bromine is going to go off and do something stupid. And I can be the friend who's there for the carbocation in need. And so even though ethanol isn't a great nucleophile, by playing this strategy, it is able to eventually have its relationship with carbon. So that's what we call the SN1 reaction. We would call this the SN1 product. Similarly, when I form a carbocation, there are solvent molecules all the way around. The neighboring carbons, also have hydrogens that become somewhat acidic. So if ethanol happens to bump into the molecule in such a way that it bumps into one of the neighboring hydrogens, that sigma CH bond can donate into the empty p orbital of the carbocation, and that can produce my elimination product. So this is my E1 product. So again, the 1 in SN1 and E1 comes from the fact that the rate limiting step of both of these reactions is that first step, the step that forms the carbocation. Once the carbocation forms, the second step is really fast. So the rate of this reaction is just really determined by one molecule alone, which is why it's SN1 or E1. So in order for either of these to occur, really what we need is a carbocation that is not too unstable. And I know that's an awkward phrase, but whenever I talk about carbocations, I don't like to talk about carbocations being stable because they are all unstable. I like to refer to them as more unstable or less unstable. So remember that A tertiary carbocation is going to be relatively stable. Um, if it's a resonance stabilized carbocation, even better. So a carbocation next to a pi bond, a carbocation next to a benzene ring, these would be even better carbocations than a tertiary. Secondary would be okay. Primary or methyl, pretty much never. So these would never happen. Secondary, that's going to be slow. Tertiary, that's going to be a little faster. I'll say less slow. And then resonance stabilized carbocation, it'll be relatively fast. Because forming the carbocation is the step that determines whether this can happen. So I'll call your attention to the fact that my mixture of products here, I got mostly substitution and some elimination. That's going to be kind of typical. Whenever you use a solvent that is a weak nucleophile and also a weak base, we will see that usually SN1 predominates, but we always have some E1 mixed in. So these two are always going to come as a package deal, as a pair. They go through a carbocation intermediate, and essentially the second step, when one happens, the other one is also likely to happen. In terms of stereochemistry, you might remember for an SN2 reaction, we saw that the stereochemistry always gets inverted. Well, with an SN1 reaction, remember, since the first step is the formation of a carbocation, and I don't know why some of my double bonds are not showing up in these notes. First step is the formation of a carbocation. Well, once I form a carbocation, it is planar. So really, I have my carbocation that looks like this. It's got an empty p orbital. And now my nucleophile can attack from above or below. Because of that, unlike an SN2 reaction that always leads to inversion of stereochemistry, here we're going to see a mixture of stereochemistries in the product. So if you attack above, you can make one product. You attack below, you make the other product. Just like the last mechanism, we're going to have to end with a depronation step. And we can make both of these products. So the key takeaway is stereochemistry gets scrambled by the carbocation. So the bottom line is you'll always get a mixture of stereochemistries. in the products of an SN1 reaction. As I said before, whenever you have SN1, you're always going to have some E1. To answer this question is pretty simple. Why might this be the case? Remember, a carbocation is desperate for electrons. So it reacts quickly with whatever is around. So if it gets collided with in the right orientation for SN1, it'll do SN1. If it gets collided with in the right orientation for E1, it'll do E1. And there's really no controlling for that. In general, there's usually more SN1 product than E1. But that will vary case to case. But if you had to predict a product, predict SN1 over E1. But I will show you one case where E1 does predominate over SN1. And that is a case where we start with an alcohol instead of an alkyl halide. I said before that I would introduce some extra leaving groups. This is going to be a case where we're introducing a new leaving group as a possibility instead of just an alkyl halide. So if I react an alcohol with concentrated H2SO4, all right, this is a strong acid. And it turns out that water loves H2SO4. So in addition to being a strong acid, it's also very hydrophilic. That's going to come into play. But it's a strong acid, so my first step is going to be to use it to protonate my alcohol. That's what strong acids do. They put protons on things. So now I have that OH protonated. Notice that makes a change from OH being a poor leaving group to H2O, which is actually a pretty good leaving group. So notice the transformation here. OH, bad leaving group. Once I protonate it, it's now become a good leaving group. And the reason is, if it leaves before being protonated, it would be OH minus. That's a strong base. We saw before when we talked about leaving group ability, way back in the SN2 reaction, we talked about leaving group ability. We said good leaving groups are going to be the conjugate bases of strong acids. So if I have OH, its conjugate base has a pK of about 6. Its conjugate acid has a pK of about 16. That is a poor leaving group. That's way too basic. But if H2O is my leaving group, its conjugate acid pK is -2. That is definitely a decent leaving group. So once I've protonated OH, I now have a good leaving group. I don't really have anything around to kick it off, so I do need to wait for it to just fall off. As we saw, sometimes happens when you have a good leaving group. Every once in a while, it will pop off and make a carbocation. Now, what's different in this case from the case we saw earlier where we had ethanol as a solvent, once I form my carbocation, it's desperate for electrons. It'll react with anything that's around. But my solution, in this case, does not contain any really good nucleophiles. The only nucleophile here is water. But the thing about the water is once it gets liberated and is able to hang out with H2SO4, it does not want to go back. Water would much rather hang out with H2SO4 than with anyone else. So I don't really have any good nucleophiles around. The only thing that's around is my conjugate base of my acid that I started with that can come and deprotonate and do this elimination, right? In this step, I have my lone parent oxygen donating to sigma star CH. Meanwhile, I have sigma CH donating to the empty p orbital on carbon. And I do my elimination. So this is a case where I do E1 mainly because I can't do SN1. I don't have a nucleophile around to do SN1. I do want to point something out about this. This is one of the first cases that you've seen where you are essentially reversing a reaction you've seen before. So earlier in the alkene unit, you saw that you could take an alkene, and if you added H2O with an acid catalyst, so you had lots of H2O, a little bit of acid as a catalyst, you made an alcohol. Now what we're seeing is if I take the alcohol and I add concentrated H2SO4, I can make an alkene, and notice a byproduct of this reaction here is H2O. So this is a reaction that we control based on what we add. If you've learned before about Le Chatelier's principle, it says if we add lots of water, it should force this reaction to the right. If we add concentrated H2SO4, which essentially removes water, we're going to force this reaction back to the left. So it's a reversible reaction. We're controlling the direction based on what conditions we put the reactants under. That's an important concept, one that will come up again and again throughout organic chemistry. All right, so overview, we've seen SN1 and E1. There's often a mixture. Usually SN1 predominates. This is one case where we can force E1 to predominate. The last thing to talk about is to put all our substitutions and eliminations together and try and decide in a given situation what is the most likely outcome. Okay, so that's what we'll do next. This next page is just a chance for you to practice this E1 mechanism using acids. There are two acids that usually get used for this. One is concentrated phosphoric acid, H3PO4, and one is concentrated sulfuric acid, H2SO4. So for practice, what I'd like you to do is draw these two mechanisms out. The first one should be relatively straightforward. The second one is a little more complicated because once you form your carbocation, something special might happen. One thing to note with the E2 reaction, we talked about how sometimes you could get a Zaitsev product or a Hofmann product, right? Where you could make the more substituted alkene or the less substituted alkene. Depending on which base you used, you might get more. I told you to always predict Zaitsev as the major product. With the SN1 reaction, the Hofmann product is pretty much never going to be possible. And the reason is this reaction is going to reach equilibrium. So once you form your carbocation, if you form the Hofmann product, that is going to be a little bit less stable than the Zaitsev product, and your reaction will go back and make the carbocation again, until you reach the Hofmann product, until you reach the Zaitsev product, the more substituted alkene. Because more substituted alkenes are slightly more stable than less substituted alkenes. So in this case, you will always get the Zaitsev product. So I'll make that note. When there's a choice, always make the Zaitsev product by E1, never the Hofmann. So always the more substituted alkene. So you'll see that in in your examples on this page. But I want you to pause, take time to draw out these mechanisms, predict the products, and then come back and I will fill them in. Okay, hopefully you've drawn out these mechanisms, and now I'm going to draw them out. First step is always going to be protonate from my acid. If you just had H plus written here as your source of acid, that would be fine as well. Your first step is going to be to protonate. That gives me a good leaving group. That good leaving group then at some point is going to leave on its own. That leaves me a carbocation. And to get to the point of what I was saying, where you could have a Hofmann or a Zaitsev product, in this case, I have two hydrogens next door that I could, or two neighboring carbons where I could remove a hydrogen. I could remove a hydrogen over here on the left, or I could remove a hydrogen over here on the right. Okay. So what I was saying before is if I remove the hydrogen on the left, that would give me this less substituted alkene product where there's only one substituent coming off the double bond. But that step where we remove the proton is reversible. So if that happens, it could go right back and form the carbocation again. And in the end, I'm more likely to remove the hydrogen from the more substituted carbon and make my more substituted product. And because this reaction is likely to reach an equilibrium between the two, it will settle on the more stable one, which is the Zaitsev product. So even if this gets formed temporarily, the less substituted product in the end, my major product is going to be the Zaitsev product every time with an E1. All right, the second case here is going to be, it's going to start out the same way. We've got a protonate. That makes my good leaving group. Leaving group at some point is going to take off on its own. But now I get into a situation that you may remember from one of the earlier modules, might have been 15 or 16, where I have a carbocation. I have a secondary carbocation next to a quaternary carbon. This is ripe for a carbocation rearrangement, where one of my sigma CC bonds is going to slide over. That will make my second tertiary carbocation. more stable carbocation by alkyl shift. And then, again, I have my choice of where I remove a hydrogen, but I'm going to remove it from the more substituted carbon. So when I remove that one, I will get this alkene product. So there you go. Hopefully you came up with that one. If you did, you should feel really good because that means you're really integrating material you learned earlier. If you didn't, that's okay. It's just a good reminder about carbocation rearrangements as a possibility. So now let's put everything together and think about how we make predictions in the case of SN2, E2, SN1, E1 possibilities. Because when you are looking at a given mixture of reactants, you want to have some way to guide your thinking. And I made this sort of flowchart that looks really convoluted, but hopefully this is just guiding your thought process. We've already done a little bit of this when talking about SN2 versus E2 possibilities. Now we're adding in the SN1 and E1. So the first question you're always going to ask yourself is, what kind of carbon is the leaving group on? Is it on a primary, secondary, tertiary, or methyl? Okay, so when the leaving group's on a methyl carbon, that is one of the easiest cases because we said when there's a methyl carbon, so if you had like CH3Br, for example, the only possible reaction is SN2. All right. Why is that the case? Well, you can't do an E2 reaction because there's no neighboring carbon to remove a hydrogen from. And you can't form a carbocation because it's too unstable. So E2, SN1, E1, none of those are possible. So if you have a methyl halide, you're doing SN2. The other case that's more straightforward is when you have a tertiary, you're leaving groups on a tertiary carbon, right? So when it's on a tertiary carbon, now the sterics are really bad. That sigma star CBr is really inaccessible. And so you cannot do SN2. So that automatically rules out SN2 as a possibility. So then the next question you want to ask yourself is, can I do E2? All right. And this is where you ask yourself, what's the requirement for E2? For E2, you need a strong base. So if you have a strong base, then you're going to do E2. Okay. If you don't have a strong base, then E2 is not really going to be possible either. So we've ruled out SN2, we've ruled out E2. This is where you're going to consider SN1 and E1, right? So if there's a weak base as your other reactant, you should expect a mixture of SN1 and E1. And we said SN1 usually predominates. So you only start thinking about SN1 and E1 if SN2 and E2 are not possible. And the reason for that is the first step in SN1 and E1 is forming a carbocation. We know carbocations are unstable. And so carbocations are going to be really slow to form. So SN2 and E2 will always be faster when they're possible. All right, so those are our two simplest cases. The next case I want to consider is, what if my leaving group's on a primary carbon? So that would be this branch over here. So if the leaving group's on a primary carbon, then you should lean toward thinking SN2. All right, there's good sterics for SN2. So usually that's going to be the case. But there is one case we said you're likely to get E2, and that's when you consider the sterics of your base. So if you have a strong, bulky base, for instance, tert butoxide is your base, then you should expect that to be an E2 reaction as your most likely outcome. Um, if you have a good nucleophile that's not a bulky base, then you should expect SN2 to be your most likely possibility. So with primary, probably going to be SN2, but if you have that bulky base, it'll be E2. And now we'll deal with the last case, which is the toughest because this is where you're going to get the biggest mixture of products. And that's if you're leaving groups on a secondary carbon. On a secondary carbon, remember, the sterics are not great for SN2. So we're probably only going to do SN2 if you have a really good nucleophile that's a weak base. So for example, CN minus would be one that's likely to do SN2 in that case, or a thiolate, something with S minus, likely to do SN2 in that case. If you have a strong base, so anything that's like an alkoxide or OH minus, then you're likely to get mostly E2 with maybe some SN2 mixed in. With secondary, we've seen you can form a carbocation there. So SN1 and E1 are a possibility, but only if your other reactant is not a good nucleophile and not a strong base. Okay, so if you have a poor nucleophile and a weak base in a secondary case, that's where you'd expect SN1 and E1. There's one thing that's not in the chart here. And that's the case we talked about where E1 would predominate. And that would be if we have an alcohol, a secondary or tertiary alcohol with H2SO4, and that's going to do an E1 reaction to make an alkene. So for example, if I have this alcohol, we saw you do H2SO4 and you get an alkene. So these other cases are considering what if I have an alkyl halide. The one way that we could force E1 to predominate, start with an alcohol and add that concentrated sulfuric acid. So that's a summary of the thought process. What I'd like you to do now is apply that to this activity. So I think you should pause the video, try each of these examples, and then come back and see my answers. So the first thing I'm going to do is characterize each of my substrates. Identify whether they're leaving groups on a primary, secondary, or tertiary carbon, or methyl. So that's my first step. Then I'm going to look at my other reactants and characterize whether they're good nucleophiles, whether they're strong bases or weak bases. So I've laid the groundwork for my thought process now that I've characterized each of these reactants. So now it's time to pick a reaction mechanism and fill in products. Um, so this first one I'm starting with, this is a gray area because, again, it's secondary and I have a strong base. So secondary with a strong base, um, I'm in the gray area, but with a strong base, I'm thinking mostly E2. Um, there will be some SN2 mixed in here, but this is going to be mostly E2. Some SN2 might be possible, but my major product would be E2. The second one, secondary with a weak base, it's a really good nucleophile. That's where I am going up this pathway. So I'm doing mostly SN2. All right, tertiary. I know SN1 is off, SN2 is off the table. Since I have a strong base, this is going to be E2. This next case is my special case where I have an alcohol and I'm adding a strong acid. And that's going to be E1. This next case I have secondary, but I have a weak nucleophile and a weak base. So that's where I am going on this right pathway to predict SN1 as my major product with some E1 as well. But SN1 is going to yield this ether as a product. This next one, I see a strong bulky base, which might make me think E2, but since my substrate is a methyl halide, I know that SN2 is the only possibility. This next one looks like the reverse of the previous one. But in this case, since the leaving group's on a tertiary carbon, sterics for SN2 are bad. So this is, and since I have a strong base, this is going to do E2. I'm going to predict mostly the Zaitsev product, which will be the more substituted one. And then this last case with the same tertiary substrate, but a weak nucleophile and a weak base, this is where I'm expecting SN1 to predominate. All right, so see how you did on that page, and then definitely check in with me if you have any questions, if there are any of those that you feel like you need clarification. That's what I'm here for. And that pretty much concludes modules 21 and 22.